This movie is about the fundamental structure of writing the mainline class of a Swing application. Swing is a collection of displayable components that you can hook together to create a graphical user interface. The main window of a Swing application has some special considerations. This example program displays an empty main window. It's a Swing mainline program, and you can tell that because it extends the JFrame class. Here, with these 3 lines of code, the size of the window is set to 200 pixels high by 300 pixels wide. The location of the upper left-hand corner of the window is set to 250 pixels from the left and 150 pixels from the top. All screen measurements in Java are made in pixels. The actual physical size is determined by the resolution setting of the monitor. The window is put on display by that last call, the one to set visible, setting it to true. You can always make a window disappear again by setting visible to false. Now, notice this code, the call to the method addWindowListener. If you're not familiar with anonymous classes, this code will look a little odd to you. It would have been possible to declare a reference to a window adapter, define a class overriding the window closing method, create an object of that class, put it in the reference, and pass the reference to addWindowListener. This would have achieved the same thing that's being done here by declaring the class and creating an instance of it in the same spot. This is sort of a shorthand technique for doing the thing. If you don't do this, the user can close the window, but the application won't know anything about it. It'll just keep running, but it won't have a window. With this little piece of code in place, your application shuts down when the window closes. Here's how it works. The window appears at the specified location on the screen, and doing this not only closes the window, but it also shuts down the application. A second common way to shut down a program is to have a menu selection named something like Close or Quit. This example has a file menu with a button labeled Exit, and that menu button will cause the program to cease execution. To construct a menu at the top of a JFrame window, a JMenuBar object is constructed. This is the bar of pull-down menus that appears across the top of the window. This example only has one pull-down menu. The tradition is that the leftmost pull-down menu be named File. With a call to add, this new pull-down menu is added as the first menu on the bar. A new JMenu item is constructed. It's labeled Exit. This class implements the Action Listener interface, so it's an action listener and can be used to receive action events from the Exit button on the menu. The menu item, which is the Exit button, is added to the File menu with the call to Add, and finally, the menu bar itself is assigned to be the menu bar for this JFrame object. Here at the very bottom, you can see the action performed method that will be called whenever the Exit button is selected. A test is made to determine which button has been selected. Now, in this simple example, there's only one button, so a call is made to System Exit, just like in the previous example. This shuts down the program. Here's how it works. Selecting the Exit button on the menu closes the application. The third common way to shut down a program is to use a regular push button. It works the same way a menu does by issuing an action event. A J button is constructed to be the Exit button. This class is added to the list of action listeners for this button. You can actually have a number of action listeners respond to the same button, but you almost always only need one. The button is then added to the window for display. The action performed method is exactly the same as it was for the menu example. It checks to see whether the selected button was an Exit button, and if so, it calls System Exit. Here you can see the exit button in the middle of the screen, and you can see how it works. Now what you want is a program that can be closed in any of the three different ways. Here's a skeleton mainline program that can be used as a starting point for building an application. At least that's what I do with it. There's nothing much new here. It's just a matter of throwing all the code from the previous examples into one class. It all works together okay. The code that defines the menu and the new window layout were separated into separate methods. That's because in a regular application, these two have a tendency to get quite large, and I like to have things organized so I can find them. As you can see, this program has both a push button and a menu. Either of them can be used to close the window. Also, the upper right-hand corner can be used. Let me mention a couple of things that you might want to consider. This program always halts with a direct call to system exit. This function call halts the JVM, so that would kill any other threads or any other programs that you may have running. That may or may not be what you want. You may want to write your own termination method and use it instead. It could simply let the window close, then have the main line of the program return. Killing the JVM is usually okay, but you may want to get out and leave it under certain circumstances. You may want your own termination method to save information to disk before you shut down. Or you could have an exclusive lock on some resource and need to release it. Or you may want to ask the user if he knows what he's doing. Anyway, once you've got your program so you can make it start and stop, it's simply a matter of adding features until it does everything else you wanted to do. Stay tuned because we've got some more swing stuff coming up. Things like dialog boxes and different types of buttons. Also, I'm going to show you a nifty way to lay out a window the way you'd like to see it. You can use any of the number of layout managers to position components on a window. Some are very simple, and they make all the decisions about positioning things for you. The ones that give you more control over the layout are a bit more complicated to use. A good compromise, and one I really like, is the box layout manager. You can use it to build almost any window you like. Here is a very simple example. This layout is simply a horizontal row of push buttons. As you can see, this class is a J-frame. That means it's the main window of a program. The actual layout of the buttons is done in the method buildFrame. First, a call is made to getContentPane to return the container of the J-frame window. A box layout manager is constructed and stored in the container, so it will become the layout manager. The layout manager is now installed in the window and waits for you to add components to its list of things to be managed. Notice that this box layout manager was constructed to be a horizontal box. That way, each component that's added to it will be inserted in a row from left to right. Here, 5 buttons are constructed and added. Each one is inserted in the container by the add method. Up until here, the buttons have only been added to the layout manager, but no action has been taken. The pack method is called to instruct the layout manager to do its job of positioning everything in the list. Back to where the method was called, after the call to buildFrame, the location of where the window is to appear is set. If you don't set this location, it appears only in the upper left-hand corner. A call is made to set visible, which immediately makes the window appear. And when you run it, there are all the buttons in a horizontal row across the window. The box expands itself vertically to fit the height of the buttons, and it expands itself horizontally to total width of all the buttons. Now, you can also put buttons in a vertical box. This is exactly the same program except for one thing. The Box Layout Manager was constructed to align the components along the y-axis. So when you run it, the buttons come out like this. But the buttons are different widths and they're flush against one side. Now some things can be done to fix all that. Here is an aligned version of the same program. A couple of method calls were added for each button. This is the addition of a rigid area component. It takes up space in the window, but doesn't actually display anything. You add rigid areas to the box just like you would add any other component. The result is they add space between the buttons and between the tops and bottoms and edges of the window. Also notice that the rigid area is 100 pixels wide. That's wider than the buttons, so the frame will be wider than the buttons and leave margins on the edges. Also notice the horizontal alignment of the buttons is set to the center of the window. The result looks like this. Alright, as you can now see, the buttons are all centered in the window and have a margin around them, but the buttons all vary in size. Here is one more version of the program with the buttons all set to the same size. Now, every component has three sizes: a minimum, a maximum, and a preferred size. This method is called for all the buttons. So effectively it makes the buttons all inflexible. As a result, the display now looks like this. The buttons are now all the same size and evenly spaced, but you can do a lot more with the box layout than just put components in a row. Let me show you a simple example. This is an example of boxes within boxes. The main window layout has a vertical box with a label at the top, a horizontal box with a couple of text areas in the middle, and another horizontal box with a row of buttons at the bottom. There are a couple of new things here I need to show you. Now, boxes always change their shape and size to hold whatever you decide to put in them. To nest one box layout manager inside another, it's necessary to put a J panel in the existing box and then assign a new box layout manager to it. Then components can be added to the new layout manager. Here you can see that two text areas have been added, separated by rigid areas. The same sort of thing was done to add the third box, the button box at the very bottom. Here you can see where a J panel was added to the bottom box and a horizontal box layout manager assigned to it. The first thing that was added to the horizontal box was a horizontal glue component. Now, glue is not a very good name for what that thing does. What it should be called is something like, put any extra space you want to have here. If you were to put in two or more glue components, they would equally share the leftover space. In this case, the glue item is added before the buttons, so the buttons are all shifted over to the right. When you use boxes to build a window, the construction is fairly easy. You can't necessarily shape it exactly the way you want, but you can get it very close. Now, coming up, I'm going to show you how to place components exactly where you want them. If you know exactly how you want a window to be laid out, if you know the size and position of all the components, you can organize the window without using a layout manager. If you're really picky, this is about the only way to get exactly what you want. I've done it this way by sketching the window on a sheet of graph paper before laying it out, and it worked out quite well. You will need to import the classes for insets and dimension because you'll use those to hold the measurements you get from the window and the components. To build the frame, you first get the content pane from the J-frame window and set its layout manager to null. You do this because any layout manager would interfere with your positioning. You need to get the insets. These are the borders around the windows. The J-frame places border decoration all around the window and in particular has a large inset at the top for the bar it places across there. Then it's a matter of creating a button and setting its size. It's the job of the layout manager to set the size of the components, and you're doing the job of the layout manager. Every component has a preferred size, and this example sets the components to their preferred size. They also have a minimum size and a maximum size, but there's usually no need to go there. The setBounds method sets the XY position of the upper left-hand corner of the button as well as its size. Finally, the button is added to the pane the same as it would be if there were a layout manager. The pack method is not called because there is no layout manager. Instead, the setSize method is called to size the window. The X and Y size of the window is calculated taking into consideration the insets on the four sides of the window. That way we get the actual size of the visible portion of the window. Here's the result. You can use this technique to place any number of any kind of components exactly where you want them. My experience has been that most windows can be laid out just fine using one of the existing layout managers, but there seems to be a rule that in any large application there is at least one window that has to be laid out this way. One important point to consider is that this layout is measured to fit exactly one window size. Most layout managers are flexible enough to do something intelligent if the window is resized. But if you want to lay out your own window this way and also allow for it to be resized, you have a lot more work to do. Your job then becomes one of checking the new window size and using that to figure out where things go. In every application, the time comes when you've got to either tell the user something or ask a simple question. You may need to ask the user whether the data should be saved or if the program should continue running. At the very least, you need to be able to inform the user of an error condition. Java Swing has the JOption pane class to make building pop-ups very easy. Let me show you a simple example. This is a simple program that only displays a window with a push button, and the push button pops up a dialog with an OK button. Now that pop-up dialog is built and displayed with one line of code, and it's done with a call here to a static method, so you don't even have to create an object. The exact form of the dialog is controlled by the exact form of the method call. This is the simplest form I'm showing you here. Let me show you. This is the main window of the program, which contains nothing but one button used to pop up the dialog. When the dialog pops up, it displays over the center of the parent window. The two arguments used on the method call were the parent window, in this case the J-frame, and the string to be displayed. Now, notice the modality. The parent window can be viewed, but it has been disabled. You can't do anything with it until you close the dialog. That's a safety measure. You can't go on with your program until the user responds. In fact, the method call that you made doesn't return until the user responds. By selecting the proper option dialog method, you can give the user more than one choice, and the method can return a code that will indicate which choice was made. The returned value is an integer indicating which button was selected. In this example, the showConfirmDialog method was used. The dialog has three buttons, yes, no, and cancel, numbered 0, 1, and 2. The method doesn't return, remember, until the user makes a selection, so the program runs like this. When you look at the documentation for the JOption dialog, you'll find a number of methods that display dialogs. Their names will tell you which type they are. They fall into one of four categories. The first one I showed you was a message dialog. It only needed an OK from the user. A confirm dialog is like the second one I showed you. It's for asking the user to confirm an action that's about to be taken. It gives the user the option of preventing the action. An example of this would be the famous "Are you sure" window that pops up. Some dialogs request information input from the user. This is usually something like a file name. I'll show you how that works here in just a minute. This isn't really a new type. It's a method of constructing a dialog. You get to choose the number of buttons, the button labels, the displayed icon, and so on. You can use it to build custom dialogs with the buttons labeled for special cases. The J-option pane dialogs all contain an icon designed to represent the type of message. The icons vary a bit from one operating system to the next, but these are the ones that show up on Windows. This is the icon for information, as you saw in an earlier example. And this is the icon shown when a dialog is being displayed to ask a question. This icon is displayed when warning the user about something. It means nothing is wrong, but something is going on the user should be aware of. And this is the icon that represents an error message. There is a total of 15 static methods for popping up dialogs. Here is an example of one that requires input. This dialog will expect a choice of one member from its list. The program specifies the title of the dialog and a prompt for input, as well as the icon specifying the message type. It works like this. One very common dialog is the file chooser. Every application of any size uses a dialog to let the user select a file to be processed and the name of a file to save data to disk. This dialog performs a simple function, one that everyone knows, and maybe that's why it's so hard to write. Fortunately, one is included with the Java Swing set of dialogs. Here is an example demonstrating the two ways of using it: to select a file to open for input, or to select the name of a file to be written to. To be able to use all its features, you'll need to import some special classes. The file chooser is the dialog itself. The filter classes are used to control the names of the files that are displayed in the list of choices. And the file class holds the description of the chosen file. You can wait until the dialog is needed before you instantiate it, or you can create the dialog ahead of time, as I've done here. Creating the object is very simple. There are no arguments on the constructor. However, you will need to set the selection mode. Here you see that I set it to display both files and directories. You can also set it for files only or for directories only. The default is to display file names only, which can be quite handy if you don't want the user to browse the disk for files. You can further limit the files displayed at any one time to those that end with a specific extension. The extension of a file is the group of characters following the last period. Files without periods are considered not to have extensions. This example uses a filter for JPEG images and another for TIFF images. You can add as many as you like. Each one has a descriptive string and one or more possible extension strings. The user can select the filter to be used. There is one filter automatically included that displays all the files. Directory names are exempt from filtering. This is the action performed method. It's called whenever you select a button. This example has only two buttons, one for open, another for save. The action for the two buttons is a little different. When the Open button is selected, a call is made to the dialog method showOpenDialog. This causes the dialog to appear with the label Open on the bar at the top. The dialog has two buttons, Open and Cancel. If the user selects a file and chooses Open, the return value is Approve Option, and we need to get the file information, otherwise no action is taken. To get the name of a file, a call is made to getSelectedFile, and the file object is returned. In this example, all that happens is its name is printed. Now the action for save is a little different. The name of a selected file is set into the dialog. Now this isn't absolutely necessary, but quite often you already have a file name and you want to include it as the default option. A call is then made to showSaveDialog, which displays the dialog with the words Save on the top bar and the two buttons Save and Cancel. The chosen file name is displayed and will be the one returned with the Save button. Here's what the example looks like. The file names that meet the filter's requirement are displayed in the window. You can change the filter anytime you want. When you select a file name, it appears in the file name list at the bottom. Oh, by the way, look at this. The file name remains in the slot because, if you'll remember, this example created the dialog and keeps it for the duration of the life of the program. So it's like an elephant, it doesn't forget. However, when you open it with the Save button, it puts a new file name in there. Notice it also has different buttons and the word Save on the bar up at the top. Now that's the basic function of the file chooser. You can do some other things like icons next to the file names and allow for multiple file name selections, but the basic operation is quite simple. You have two ways that you can ask the user to choose a color. Which of the two you use depends on the needs of your application. Let me first show you the Color Chooser dialog. The main window of this example has two buttons. They both pop up a dialog that allows for a color choice. The color returned from the first button changes the background color of the buttons. The second changes the color of the text in the buttons. Now here's what happens when you press a button. The text you pass to this static method is the text shown on the bar at the top of the window. The third argument here is the initial color. In this example, it's the foreground color of the button, B1. Notice that a color is always returned. If the user cancels the pop-up, the initial default color is returned, so you always need to set the default color. In the same way, selecting the second button, the button labeled Letters, will cause the foreground, the lettering of the buttons, to be changed. Here's how it works. The main window of the application is nothing but a couple of buttons. We can change the background color of the buttons this way. The first view you get is that of swatches. These are some commonly used colors for you to choose from, but you can pick the colors in other ways. If you prefer, you can select the 3 RGB values for your color. You can see the default button color value shown here. It's almost white with all 3 RGB values close to their maximum. Now, changing the color here also changes the color settings for the other two views of the color. Speaking of the other two views, look at this HSB. The letters HSB stand for hue, saturation, and brightness. It's an attempt to display colors in a more intuitive way. It's different, and you'll need to fiddle with it a bit to see which one you like best. For this example, I'll just pick a swatch. Notice how when you pick a color, examples of it are displayed at the bottom of the window. The examples are displayed next to some black and white areas so you can get a better idea of what it will look like in your application. The Reset button always restores the default color, and the recent colors allow you to go back to a color you previously selected. The OK button causes the dialog to return the color that you've currently selected. You can see that this turned the buttons blue. The second button will change the color of the letters. As you can see by the preview, the default color for the letters is almost black. Choosing another color will change the letters. There, they've changed. There is another way you can use the color chooser. It can be included in one of your windows, just like you would include any other component. You will need to import the Change Listener interface and the Change Event class, and you will need to implement the Change Listener interface. Now this example is a window with a label at the top and the color chooser as a component at the bottom. A new color chooser object is constructed with the foreground color of the label as the initial color. Just like with a button, the foreground color is the color of the letters. You want to be notified when a color selection has been made, and that is done by the color selection model. So you get the address of the color selection model and add this object to the address of those objects that will be notified when a color selection has been made. This method is called then every time a change of color has been selected. The returned color is then inserted into the label as the new foreground color. It works like this. This is the same color selection as before, but there are no buttons at the bottom. Each time a color is selected, the change shows up immediately with a label at the top. Up until now, all the buttons that we've dealt with have been momentary. When you clicked on one with the mouse, the action event was transmitted, and when you let go, the button popped back to normal. But there are two kinds of buttons that don't pop back. When you push them, they stay pushed. The first of these is called a checkbox. Checkboxes show up on the display as a list of items, and you can choose as many of them as you'd like. This example isn't very fancy. It just shows you the bare essentials of checkboxes. You will need to implement the Item Listener interface only if you want to receive notification of every click of the mouse on a checkbox, and that's not absolutely necessary. For some applications, it is sufficient to only read the settings of the checkboxes later when the information is needed. This example reads the settings when they are made. Now, this program uses a box layout with a label at the top and a list of checkboxes below it. The label indicates which boxes have been checked. The checkboxes are labeled A, B, C, and D. Each checkbox is constructed with a label starting with its letter. At the outset, the checkboxes are all set to being selected or checked. This object is listed as the Item Listener for the checkbox, so we'll be notified of all its changes. This is the method that's called each time the state of a checkbox changes. All it does is build a string of text for the label that indicates which of the checkboxes are selected. And here's how it works. It's a very simple window with no borders or margins. That was to keep the example source code as simple as possible. The 4 checkboxes are named for animals. Well, except for that last one. I couldn't think of an animal that starts with D, but there was a guy in my school who I always thought was a kind of a gorilla. But you can see how changing and selecting and deselecting the buttons changes the label at the top. The other kind of button you can set is the radio button. In a group of radio buttons, only one can be selected. Here again, you only need to implement the Action Listener interface if you want to track each click of the radio button. It's usually easier just to wait till the end and then read them all at once. The layout is the same as it was before. A label at the top is used to indicate which of the buttons has been selected. A button group object is constructed. The radio buttons are all related to one another, and the way you relate them is by adding them to the button group. The button group object will automatically deselect all of the radio buttons whenever you select one. Each time you create a radio button, you specify whether it's the one to be selected, true or false, and you add it to the group of radio buttons that are to work all together. All the radio buttons but one should be unselected. Here at the very bottom is the method that's called every time the radio button is selected by the mouse. The label is assigned text indicating which button has been selected. Now this method call returns the button that has been selected. The information is used to print out the name of the button. Here's how it looks as it runs. As you can see, only one button at a time can be selected. Also notice that the printed button name is the name of the one selected. It's never the one that becomes deselected. There comes a time when you need to have the user input a small amount of text. It's most common for the user to be required to enter a username and a password. I'll show you a couple of components designed so you can set this up. The JText field component will accept a single line of text typed in by the user. In this example, the prompt is for a username. Now, this example doesn't really do anything fancy. It uses the JText field as a component to accept the input text. The JText field object is constructed with the number 32 as its only argument. The number is the size of the text field. In this case, the size is the number of characters, not the number of pixels. The actual size in pixels will change if you change the font. If you need to know the actual size, you'll need to call getPreferredSize to return the number of pixels. I do that here in this example because I set the size of the window according to the size of the components. Here is the other text input component in this example. It's a special subclass of JText field called JPassword field. It's designed solely for the input of passwords. It has become accustomed to assume that the user is in the room with a nosy, dishonest person who would read the password if it appeared on the screen. This component works a lot like JText field, but it doesn't echo the input characters back to the screen. At the bottom of the window is a login button. None of the text input in this example is read from the components in the window until the login button is clicked. This object is added to the list of action listeners for the button. So the action performed method is called when the button is clicked. The getText method of the JTextArea object is called. It returns a string object containing the username. The getPassword method of the JPassword field object is called. The password is returned as an array of chars. The documentation says this was done for security and that you should specifically erase the contents of the array when you're through with it. But I don't quite see the danger. Apparently this was done with a more primitive language in mind, like C or C++. In Java, all memory is erased before it's reused anyway. Here's how the program works. As you can see, the characters of the name are echoed to the screen as they are entered. A tab character takes you to the second field. But notice that the characters of the password are not echoed. But as you can see, both the name and password were output from the print statements in the program. But there are times when you need to enter more than one line of text. In that case, you need the JTextArea component, which is a rudimentary text editor allowing for the entry of blocks of text. Here you can see the creation of a new JTextArea object. It has 12 lines of text, and each line has 40 columns. I don't do all the fancy stuff in this example, but you can set the font to whatever you want. You can insert the initial text if you like. You can set it to accept long lines or to automatically wrap the text. Now, it is possible to monitor the characters as they're typed in, but in this example, I have added a push button, and the action performed method is called to get the text from the component. It does so by calling getText and returning a string object. Here's how it works. You can type in the text freely according to whatever the rules are that are set up. When the Enter button is clicked, the entered text is displayed by the program. One of the simplest components to use is the combo box. You can simply declare yourself an array of choices and use that in the construction of the combo box. The component then handles the pull-down list and display of the current selection. All you have to do in your program is read the result. This example uses a JComboBox component to let the user select from among the names of the planets in our solar system. You can add the items to be chosen from one at a time, or you can put them in an array as in this example. The list of items to be chosen from in the array is included on the constructor. In a combo box, one of the items is always shown as being the one selected. You can specify the index of the default selection. If you don't specify, the default is item 0, the first member of the list. This class implements the Action Listener interface, so it can be added to the list of action listeners for the combo box. This is the method that's called every time a selection is made from the combo box. This method displays the name of the selected item and the index of the selected item. Here's how it works. Here you see the original appearance of the combo box with just the selected item showing. If you click the button, you get a list of items. Notice the scroll bar that appears with the list. This is what happens when there are more items in the list than can fit into the display. The combo box has a maximum row count that limits the number of items it displays, and you can change that if you wish. The default setting is shown here. You can select any member of the list, and you can see that both the string and the index of the selection are available inside the program. Let me show you a slight variation of the combo box. It is possible to edit the contents of a combo box. This example is exactly like the previous one, except for one line of code. This, the call to set editable. This call makes it possible for the user to enter a name as well as select one that's already there. Now you can enter a name like this. You can see that the program got the name. It was not a member of the list, so its index is -1. Notice that even though the new name was entered, it did not modify the list. You can display large tables of data by using combinations of the Box Layout Manager to form the rows and columns, but you could also use the JTable component and let it do the layout work for you. To do it, you need to use both the JTable component and a JScroll pane. The two of them work together. You can't reliably display a JTable without using a JScroll pane. You declare the column headings as an array of strings like this, and you declare the data for each cell in a two-dimensional array like this. This array can hold any object that can be converted into a string for display. In Java, every object has a string form, so any kind of object can be used. In this example, the first column is made up of integer objects, and all the rest are strings. You use the data and column array declarations on the constructor. This builds the table of the right size according to the size of the data arrays. Then you set the size of the display of the components. The size you choose will determine the height, the number of rows displayed, and the overall width. In the width, all the columns are displayed. The width is divided evenly among the columns, so they'll all be the same size. This method call makes certain that the table expands to fill the space assigned to it. This is where the partnership with the JScroll pane comes in. You create a JScroll pane using the table as an argument on the constructor, and it is this pane that then is added to the display. There's the table with the column headings across the top. Not all the rows are displayed, but the scroll bar on the right allows you to see all the rows. Notice that the columns are all the same width. You can actually vary that, but in an odd sort of way. Now this program is exactly like the last one, except that a few lines of code that have been added. This for loop has been inserted. Before the loop, a call is made to get the column model. Inside the loop, the column model is used to retrieve the table column object for each of the columns. Inside the loop, the width of the first two columns is set to 50, and the width of the other columns are all set to 100. Now these settings are relative, not absolute. The actual column width is set automatically, but the width allocated to each one is relative to the width numbers assigned to them. That is, the first two columns will only be half as wide as the others. Now, here's the result. Here it is, the same table as before, but the first two columns are only half the width of the other three. You can set it up so the user is able to select data, but doing so isn't as straightforward as maybe it should be. To receive selection events, you need to implement the List Selection Listener interface. Now this is the same program again, with a few lines of code added. This code was added so the program will respond when the mouse selects any individual cell data. These two lines of code set up the JTable component so it will respond to the mouse one data cell at a time. These two lines of code extract the selection model from the table and add this object to the list of those notified when the row number changes. In similar fashion, the selection model of the column model is added to the list, so this object then is notified when the column number changes. Here is the method that is called each time a row or column number different from the current one has been selected. Notice this method call here. This method is called once when the mouse button is pressed and again when it's released. The getValueAdjusting method is true only when the mouse button is pressed, so this call eliminates duplicates. If duplicates don't bother you, you can leave this line out. Now this method is called every time a row number changes and again every time a column number changes, so when they both change, it's called twice. Again, if duplicates don't bother you, you can leave this out. This example just prints the row and column numbers and the contents of the table at the location. Here's how it works. Any cell selection you make is reported to the program. By the way, it is possible to read information entered by the user. The strings you read from the array will be the string as entered by the user. The JTable component can be used for both displaying and entering data, but some components are only for displaying information. The next lesson shows you an example of that in the form of a progress bar. Some tasks take a while to complete, and you need to let the user know that something is happening. Ideally, you can also tell the user how long it's going to take. One common way of doing this is displaying a progress bar. Users are really quite patient and will wait for a task to finish as long as they don't think the program has crashed. A program that demonstrates the operation of a progress bar must have a task running in a separate thread. It's this separate thread that advances the progress bar. The degree of completion is denoted by a number. Now, you can have the progress bar advance from any number to any other number, but I have always found it clearest to progress from 0 to 100. You will need to import the JProgressBar component, which can be displayed in your window the same as any other component. On the progress bar, you specify the low and high numbers. This progress bar will go from 0 to 100. The setValue method is used to specify the amount of completion, so it's set to the beginning, to 0. This call causes the current value, the degree of completion, to be painted in the middle of the progress bar. A new task is constructed and started. Notice that the progress bar is passed to the task. It's the job of the task to adjust the completion value as it progresses. This is the class that runs as a task. It implements the runnable interface so it can be run as a separate thread. This run method is the executable loop of the thread. It doesn't do much. As long as the Boolean running is true, it sleeps for 0.2 of a second, then it updates the completion number in the progress bar. Once the completion number has reached 100, the task stops running. Here's what it looks like. You can see the completion value being displayed on the progress bar. Actually, you can run the numbers from any number to any other number, and the displayed value would be from 0 to 100%. When it reaches the end, the task stops running, but the progress bar is still displayed. Now, you may be in a situation where you don't know what degree of completion you've got, but you can still use the progress bar. You can use it in indeterminate mode. Now, this form doesn't depend on any information from a task. All you do is display the progress bar. The construction is the same as it was before. You specify a range, but it doesn't matter because you won't be using it. You call this method to set the mode of operation of the progress bar to indeterminate. Then you just display it. It looks like this. It will run back and forth this way as long as you keep it on display. This has one drawback, however. It will continue to look exactly the same even if your background thread has crashed. If that ever happens, your user won't trust your program to run again. It is normally better to display a changing completion value, even if it is an approximation. Here is an example of using the indeterminate mode and displaying a value at the same time. Now, this is exactly the same as the first example, except for one thing. This method call right here. to set the indeterminate mode. It looks like this. You can see that the value displays just fine in indeterminate mode. You can have the value jump around, even run backwards, and it will give the user the assurance that something is going on, even if there's no way to tell how close it is to being finished. If you prefer, you can have the progress monitor pop up as a dialog. The first argument on the constructor is the parent window, the same as with any dialog. The second argument is a string to be displayed in the window. The third is an optional string, the note. I'll have more about that here in a minute. After that, you specify the range of values for the progress bar, like we did before. And you set the starting value to whatever you want. You pass the monitor to the task, the same as you did earlier with the progress bar, and you just start setting values in it and it displays itself. If you want running numbers, you will have to specify the string you want displayed with a call to set note. Also, the dialog has a cancel button which can be used to terminate the task. Here's how it looks when it runs. The monitor shows the values because they are changing. You can cancel the task at any time or wait until it's finished. Either way, the dialog closes. Coming up in the next lesson are sliders and spinners, two ways the user can change values using the mouse. Sliders and spinners both do the same things. They allow the user to choose one value from within a preset range, but they do it in very different ways. First, let me show you a date spinner. It's always a problem to set things up so the user can enter a date because of the problems of validating the day of the month with the month name, and then there's leap year and so on. The spinner date model component has partially solved this problem. To use it, you'll need to import both the JSpinner and the spinner date model classes, and you'll need to implement the change listener interface. You begin by creating a new spinner date model object. Now you can specify the default date, or you can create it this way with no arguments, and it will default to the current date. It is to this model object that you add the change listener, so you will be notified when the user changes the date. But you create a different object for the display. You create a JSpinner object using the date model as the argument on the constructor, and it is this new JSpinner object that you put on display. This is the method that's called when the user changes the displayed date. Now this example doesn't do anything but output the date. Here's how it works. It starts out by displaying the current date. You can make an adjustment to individual parts of the date. Whenever you change something in the displayed date, the other parts of the date change as necessary to keep the date valid. Now you can see that this uses a 2-digit number to display the date, so it can only display the years in a 100-year range. It displays the years 20 years into the future and 80 years into the past, so it won't work for everything. If you need a wider range of dates, you'll have to come up with some other way. Probably the most common form of a spinner is one that lets the mouse choose from a range of numbers. To do that, you will need to import a different model for the spinner number model. You will still need to implement the change listener. You construct the spinner number model by specifying first a starting value, in this case 180, and a range 0 to 360, and a step. The step is the amount the value will move with each click of the mouse. You create a JSpinner object and add it to the display the same as before. In this example, a second component, a rotor, is added to the display. All it does is draw a line slanted in the direction specified by the angle value of the spinner. In the state changed method, the value is retrieved from the spinner. It is a number, and it comes to you in the form of an integer object. The value of the integer is passed to the rotor object, which is repainted in the position specified. Now, here's what that looks like. You can see the spinner here at the top of the window with its initial value of 180 and with the two buttons that are used to adjust the value. Selecting and holding one of the buttons will move the value through its range. Or you can simply enter a number directly. Another component that does exactly the same thing but in a very different way is the slider. The slider is easier to program. You will need to import the JSlider component, and you will need to implement the Change Listener interface. The construction of a slider is straightforward. This example uses a horizontal slider that has a range of 0 to 360 and has an initial setting of 180. This slider is to display tick marks along its length. It will display a major tick mark at 45 and a minor tick mark at every 10. This object is added to the list of change listeners, and the slider is added to the display. A rotor is added to the bottom of the display. When the value is changed by the user, the new value is used to set the position of the rotor. Here's how it works. You can see the slider sitting at its midpoint, 180. Unlike the spinner, you are not shown the numeric value of the current setting, but it is much easier to set the value of a slider. Sliders and spinners do basically the same thing. Which one you use depends on what your application needs. With one you get speed, with the other you get accuracy. The next lesson is about decorating your application. There are several ways you can use icons to decorate your display. You can use an icon to decorate many of the displayed components. Most often you will see this done on menu buttons, but you can do it with any button. It's quite easy. Let me show you. This example uses an image instead of text as the displayed portion of a button. The image icon class makes this quite easy to do. There are different kinds of icons. There is even one kind where you paint the image on it yourself, but this one lets you load the image from a JPEG, GIF, or PNG file. You create the image icon by naming the image file you want to use. If you prefer, you could specify the URL of an image file on the internet, or if you have image data already loaded into memory, you can use that. The image icon class contains a media tracker, and it uses that to monitor the loading of the image. You use the image icon in the construction of the button the same way you would normally use text. This example also uses another button, one with simple text. Here's what it looks like. As you can see, the image used in this example is the picture of an old license plate. The button responds to the click of the mouse by darkening the background color. The icon image itself doesn't change. You can also see that the size of the button is determined by the size of the image. If the image had been half the size of the screen, the button would have been made big enough to hold it. You can either scale all your icon images before you use them, or you can scale them when you load them. Just changing the size of the button won't work. All that does is clip the image and display what's left. To scale the image, you will first need to extract it from the image icon object. I have devised a method for the purpose of loading scaled icon images. This way, I can have a number of buttons show up with icons all the same size. The method creates a new image icon object just the same as before. The image object is then extracted from it and scaled, and the new image object is stored in the image icon. By the way, if you set either width or height to -1, the scaling is done in such a way that the aspect ratio remains the same. That's usually not important with icons, but it can come in handy. The button is then constructed in the normal way, using the scaled image from the method. This is how it looks. There you can see that the display looks exactly like it did before, except the image in the button has been scaled to a more button-like size. With very little effort, you can combine text with the icon in the button. It is simply a matter of including text with the icon on the constructor of the button. Now it looks like this. As you can see, the button resizes itself for both the text and the icon. This is a common technique when defining menu buttons. Next, we'll be looking at menu bars and menu buttons and some other components you can include on a menu.